Hello everyone and welcome to CSEN 503 Introduction to Communication Networks. This is Dr. Amr Al-Mogi. In our last lecture, we finalized the discussion of the application layer. We discussed web caches and we discussed the DNS system. And we saw how the DNS system is a hierarchical database that enables a device to obtain the IP address of a destination that it wishes to contact. This actually ends the discussion of the application layer, and today we are going to start the discussion of the layer below that, which is the transport layer. In this discussion, we would like actually to know, let's say, the main objective of the transport layer, its main functions, and we will study the two transport layer protocols that we have in the internet, which are TCP and UDP, and we will study all the features and services that they have. We have discussed actually the transport layer before briefly. When we were discussing the protocol stack, we had the exact example of the building that is actually sending letters. And we said that the transport layer acts as a secretary. It collects actually the information or the data that the application generates or the application layer generates, and it breaks them up into smaller segments. And each segment is then transformed or made into a packet. And the transport layer will take one of these segments and then add to it the transport layer header, and then give this segment as well as the transport layer header to the network layer below, which then will add the network layer header and so on. So the transport layer provides a logical communication between app processes running on different hosts, meaning that if you have a process running on host 1 and you have a process running on host 2, the transport layer below host 1, below the application layer at host 1 and host 2, will enable logical end-to-end transport, meaning that data that is generated at the application layer of host 1 will actually be given to the transport layer, and the transport layer will actually continue with the process until it actually reaches the transport layer in H2, which then it would give it to the application layer in H2. Okay, so we can say that there is a logical or a virtual communication between the transport layers at H1 and H2, and this communication is enabled through the transport layer header. The transport layer in H1 will add a header to the application message. This header will actually contain some information that the transport layer in H2 will read and will accordingly provide some services to the application, as we will see later in this lecture. Okay. Okay. So we know that in the internet we only have or we have mainly two transport layer protocols, which are TCP and UDP. TCP is short for Transmission Control Protocol. This is, let's say, the full protocol that provides a wide set of services. It includes connection-oriented communication. So if you are using TCP, you cannot actually just send data right away. You have to establish a TCP connection first. It provides reliable data transfer. As we will see in a little bit, this is done using actually acknowledgements or feedback from the receiver back to the sender, and provides also flow control and congestion control. This is TCP. It's the full protocol that provides actually a set of services to the applications if they choose to use it. The other protocol is UDP, or the user datagram protocol. It's an empty protocol. It doesn't actually provide any of these services into the application. So we can say it's just an extension of a best effort IP protocol at the network layer. And we said before that even though UDP is an empty protocol, it has some advantages. First of all, it doesn't impose any delay to the application or on the application as TCP, because TCP has all these set of services that may actually end up causing delay. So UDP doesn't have that, which means that real-time applications will end up preferring UDP because of its slow delay. And also the other reason for having a protocol like UDP is that it's a blank slate protocol, meaning that it's an empty protocol that you can write anything on top of it. So if you want a particular service, you can use UDP and then implement the services, this service at the application layer. It's important to note that neither TCP nor UDP offer any guarantees or any services related to delay or bandwidth or even security. If you want security, there is actually an additional protocol to TCP that is called TLS, which provides the security. Okay. So TCP is the full protocol, UDP is the empty protocol. Both of them actually have to support the service or the functionality of multiplexing and demultiplexing. When we were discussing the protocol stack, we said that the primary job of the transport layer is to actually give the right piece of data or the right message to the right application process that needs it. So if you have, for example, a browser at your device and you're opening many tabs, each tab is actually downloading a different web page. So when you send HTTP requests from all these tabs, the responses are going to come, and the transport layer will be the one that sends actually the right resource to the right tab according to who requested it. This is done using port numbers, as we will discuss in a little bit, but this figure here shows actually a rough idea as to what is happening. For example, here host 1 is actually generating a message. There is process P3 that is generating a message, and the message will have source and destination port number. At the same time, host 3 is also generating a message P4, and both messages are actually sent to host 2. There are two application layer processes that are running, expecting to receive these two messages. So it's up to the transport layer in host 2 to send the right message here. The right message from process 3 is given to process 1 in host 2, and the message from process 4 will be given to process 2 in host 2. So the transport layer in host 2 is the one responsible for sending the right message to the right application process, and this is done using port numbers. So this is actually the first piece of information that has to be added to any transport layer header, regardless of whether it is a TCP header or a UDP header. These are the source and destination port numbers. And in both TCP and UDP, the source and destination port numbers are each 16 bits long. Okay, so you can have roughly 2 to the power 16 different application processes running it in your machine at the same time, which is of course a very huge number. Now we can actually start to discuss how are port numbers chosen. When we discussed the application layer, we discussed how IP addresses are found out. This is using the DNS system. So now we know that when you want to contact a server and you don't know its IP address, but you only know its URL, for example, you want to send an HTTP request, before you send the HTTP request, you have to go through the DNS database and send the DNS query so that you obtain the destination IP address. And the source IP address is, of course, given to you by the network. So now we know how the network layer header will add the source and destination IP addresses. Now we will discuss how the transport layer adds the source and destination port numbers. Okay. We will discuss first how UDP does it because it's the simpler one, and then we will extend the discussion to TCP. If we want actually to have an application process generating a message, and it will give it to the transport layer, and the transport layer will add the transport layer header. So now the transport layer has to choose the source and the source port number and destination port number. The source port number is actually easy. In both TCP and UDP, the source port number is actually just chosen by the sending device. So if this is client A or device A and it wishes to send a packet to server B, it will actually choose its own source port number. Now, how will A choose the source port number? Is it actually just chosen at random? Is it any number that falls between 0 and 2 to the power 16 because the port number is 16 bits? The answer is that the source port number has to be unique. However, it has to be unique only within client A. That means no two processes in client A should have the same port number. The reason is that when the response comes back, it is going to come back addressing this port number. That means the transport layer in A, once it receives the responses to these requests, the responses are going to identify an application layer process using the source port number that A has chosen. Okay. And so in order for A to be able to differentiate between the responses coming to the different application layer processes, it has to give each one a different source port number when it is sending the packet. So when A generates a packet at the application layer and gives it to the transport layer, it adds a source port number that is unique within this device. Okay. So this is the source port number. The destination port number is actually also quite simple. Basically, okay, That means the port numbers can actually range from 0 to 65,000 and something. In the internet, the first 1,000 numbers are reserved. They are known as well-known port numbers. The well-known protocols, the protocols that are widely used, have a reserved well-known port number. For example, if you're using HTTP, the port number is 80. That means any HTTP request that you will send will have port number 80 at the transport layer. If you're using DNS, I think the port number is 53. That means when you send the DNS query, the port number will actually be 53. And by the way, DNS uses UDP at the transport layer. That means there is no connection between your device and the local DNS server or the root or TLD or authoritative DNS servers. And this is because you want the DNS process to be actually fast. If a DNS query gets lost or it gets dropped at a router, then it can just be retransmitted later. Okay, so the first 1,000 port numbers, whether in TCP or UDP, actually, the first 1,000 port numbers are well-known port numbers. Okay, and each protocol has one of these. Each protocol that is actually one of the widely used protocols like HTTP or DNS or SMTP, which is used for email. I think its port number is 25, something like that. So these well-known port numbers are already saved in your device. That means when you are using a particular protocol, you will know its destination port number if it is a well-known port number. If it is not a well-known port number, that means it is, for example, a proprietary protocol, something like Skype or a different application that is actually using its own protocols. It's not using, for example, HTTP or SMTP or DNS. It's not using actually any of these protocols. Then the destination port number will actually be embedded in the application itself. That means either it's a well-known port number or it is something that the application provides to you. In either case, the destination port number will be known to the client. Okay. So now the client has the source and destination port numbers. It can thus formulate a transport layer header and then give the packet to the network layer, which adds a network layer header and so on. Now this packet here is sent from A to B. This is the UDP protocol. That means there is no connection establishment. A sends the packet directly to B. So now B receives a packet with these source and destination port numbers. Once it wishes to respond, it will also create a packet at its application layer, and it will give this packet to the transport layer at B, which will add a transport layer header, which has also to include a source and destination port number. In this case, the source and destination port numbers will simply be flipped. That means whatever was the source port number in the packet that was generated by A becomes the destination port number in the packet generated by B. And whatever was the destination port number in the packet generated by A becomes the source port number in the packet generated by B. Because B is a server, B will be always on. That means B will have something called a listening socket. It is always on, it is always open, and it always has the same port number, which in this case is 46428. That means any device, if there is a different client C, for example, wishing to send a packet to B, it will generate its own source port number and will have the same destination port number, which is 46428. Okay. Now, what happens if by coincidence A and C will choose the same source port number? That actually is not a problem. It would happen by coincidence, and there is a low probability that this will happen, but there is no problem because when B generates a response, it's going to send it to the IP address of either A or C. So at the end of the day, the packet is going to go to either A or C and will carry the source port number. Even if it is the same, it is not important because the source port number needs to be unique only within a device, not globally. Okay, so when this response comes back to A, it will carry the source port number of B. So the device A will know which application process actually generated this response, and it will look at the destination port number to know which application process at A generated this message, and you will find that it's the same source port number as the one that was entered in the original packet, and so it will know how to give the packet to the right application process. Okay, so this is for UDP. TCP is a little bit different. Because TCP is connection oriented, this phrase connection oriented means that there is actually a logical connection between the client and the server. And what we mean by a logical connection is that the client and the server will actually save some information about each other. For example, later we will learn that a TCP uses something called sequence numbers to number the packets so that you can have reliable delivery. So the server has to actually remember these sequence numbers in order to know which packet has arrived correctly and which packet needs actually to be retransmitted. So the client and the server need to save some information about each other. They need to associate the packet that is coming with a particular client. This was not the case in UDP because UDP is not connection oriented. That means when this packet here arrives at B, it's just actually like any other packet. It could be up to the application layer to differentiate which packet actually belongs to which user. That is fine. However, the transport layer, if it is running UDP, it doesn't actually need to differentiate between the users. TCP does. Okay. So because TCP needs to do that, the socket is now identified not only with the source and destination port numbers, the socket is also identifiable using the source and destination IP addresses. So a socket in UDP is only identified using two pieces of information, which are the source and destination port numbers. The socket in TCP is identified using source and destination port numbers plus source and destination IP addresses. And so what will happen here is that the server, first of all, will be listening on the well-known port number. Okay, if it is HTTP, the port number is 80. Once it listens to the well-known port number and receives a connection request, it will create what is called a communication socket. So it will listen to the TCP connection request on the listening socket, and once it gets a request, it will create a communication socket. This communication socket will be identifiable using this for tuple. Okay. Now, again, if this is client A and it wishes to send a TCP request to server B, the TCP request is going to carry a source port number, which is again generated by client A, and it has to be unique within all the processes in client A. The destination port number is the well-known port number. So if it's HTTP, the destination port number is 80. And the source IP address and destination IP addresses are inserted in the network layer anyway. So this TCP request will make its way to B, and it will generate a communication socket and respond with the TCP response back to A. Okay. Now A can start sending packets, and the packet is going to be identified at B using these four tuples. Why do we need the source and destination IP addresses in this case? Imagine this scenario where you have here client C, okay, happened to have chosen by coincidence the same source port number at A. So it chose 26145. In UDP, this was not a problem because you did not actually need to differentiate between the devices at the transport layer. Here it is actually a problem. Now, these are two packets that are carrying the same source and destination port numbers, yet B needs to know, or the transport layer at B, TCP at B, needs to know which packet actually belongs to A and which packet belongs to C. Why? Because as we said, the TCP offers a set of services. So it offers, for example, reliable transport. If it wants to give feedback to A or C that the packet has arrived, it should know exactly whether this packet came from A or it came from C. This wasn't the case in UDP because there are no services offered with UDP. Now, if A and C by coincidence just happen to choose the same source port number, this will not actually be possible to identify them at B, which is why B needs to use the source and destination IP addresses to identify a socket. Now, the source and destination IP addresses of A and C will definitely be different because no two devices actually have the same source and destination IP addresses. And so even if they end up choosing the same port number, they will have different IP addresses, and B will actually be able to differentiate between them. In another example, if A has actually two TCP connections with B, for example, HTTP allows you actually to open up to 6 parallel connections to download resources, and each one of those connections will have a different source port number. Okay. In this case, B will still actually see this as a different socket, a different port, because it has a different source port number. Here, even though the source IP address is the same, because now the reason, again, we are having source and destination port numbers as well as source and destination IP addresses to identify a socket is that TCP has actually a lot of services to offer to the application. And the services are offered per connection. That means the transport layer at B has to actually be able to differentiate between the connections that it has. And so it needs all these information, source destination port number, source and destination IP address, to be able to differentiate between the connections and accordingly offer the services to each of these connections independently of the others. Okay, so this is how source and destination port numbers are chosen in TCP and UDP. And now we can actually, by the way, this is just a summary of which internet applications use which transport layer protocol. We know that applications that require reliable data delivery typically will go for TCP. Real-time applications will typically go for UDP. Now we can actually take a look at the header that is added by UDP. As you can expect, the header doesn't actually have a lot of information because UDP doesn't actually offer a lot of services. And so the header is nearly empty. It just includes the source and destination port numbers. Each one is 16 bits. And then it also includes the length of the packet in in bytes. This includes also the length of the header, and the length of the header is fixed. It's just 64 bits. Then there's something called the checksum, which is used to check for errors if this is something that the application would like to use. But UDP itself doesn't actually have any reliable delivery mechanism. So we know UDP is used by applications that are real-time in nature or that do not care about data loss. So DNS, for example, is one of these applications, as we said before. So it uses UDP so that you don't actually suffer a lot of delay in obtaining the IP address of the destination that you want to communicate with. And this will actually be all the discussion about UDP. And now we can start actually discussing TCP. TCP is the full protocol. It's the one that actually has the set of services. And so our remaining discussion of the transport layer is going to focus only on the services in TCP. So the first service, as we know, is multiplexing and demultiplexing. That means TCP also has port numbers, and we saw how they are chosen. And so just like UDP, TCP is able to give the right packet to the right application process using the port numbers. The first service that we will discuss is reliable data transfer. It's a very important service that distinguishes TCP from UDP. And in reliable data transfer, the objective is to do what you actually see in this slide. In communications over the internet, you have a sending process and you have a receiving process. You have a process that is sending data and you have a process that is receiving data. Ideally, you want actually to see the packets that are generated sent over what is called the reliable channel, meaning that what you send through the channel ends up making it through intact without errors and without actually the order being changed, okay, at the receiving process. That means what you send is exactly the same as what you receive. We know that in the internet, things are not that clear-cut. Errors happen, problems happen. And so what will happen is that the packets will actually have errors. They will be lost. They will arrive without order. And so the transport layer in reality will provide a reliable data transfer mechanism that acts as if the communication between the sender and the receiver is actually through a reliable channel, while it is actually through an unreliable channel. So we have reliable data transfer protocols that are running on top of this unreliable channel, whatever it is, so that at the end of the day, the application processes would see as if the channel is reliable, while in fact it is not reliable, and it is the reliable data transfer mechanisms at the transport layer that are making it seem this way. So how is this done? Let us say that you have a sender A sending a packet to receiver B. The packet is sent blindly. That means A will have no idea whether B has received the packet or not. And so A will have no idea whether it needs to retransmit the packet or there has been an error or a router has lost it or anything that has happened on its way. In the internet, the only way that A would know that the packet has been delivered at B is that B will actually send some feedback to A saying that the packet has in fact been correct. This feedback is called an acknowledgement. And this is actually the core of reliable data transfer mechanisms. Feedback from the destination back to the sender. Now, the acknowledgement packet is just like any other packet. That means if there are many routers between A and B, these routers will carry the data packet from A to B, and they will also carry the acknowledgement packet back from B to A. Okay, so things seem simple, but there are actually many issues that we have to discuss about reliable data transfer. And before we discuss how TCP implements reliable data transfer, we will discuss a much simpler reliable data transfer mechanism, which is called stop and wait. Okay, this is not what TCP uses, but I will discuss it just to actually clarify what we mean by reliable data transfer. So up to this point, A sends a packet to B, B sends a packet back to A. If the channel is completely reliable, that means the channel never produces an error, then you will not even need the acknowledgement. You can actually just send packets and you know that there are no errors, and so the packets will be delivered. But because there are errors, you need this feedback. Now the question is, what would happen if the packet sent from A to B is lost? Or even if the acknowledgement sent back from B to A is lost? Then A will again have no idea that the packet has actually been correctly delivered. And so it will need to retransmit. The question now is, how long should it actually wait? How long should it wait before it retransmits the packet? The answer to this question lies in a timer. When A sends the packet to B, it will start a timer. Once this timer expires, A will assume that the packet has not been delivered to B. It could be that the packet has been delivered, but the acknowledgement is lost. A will not care. Okay? Once the timer expires, A will assume that the packet is lost and will retransmit the packet again to B. Now, if the original packet is lost, then this is actually fine. The retransmitted packet will make it to B, and then B will actually send an acknowledgement back to A, and then A will cancel the timer. That means A will start the timer when it sends the first packet. If it gets lost, the timer will expire. It will retransmit and will start the timer again. If there is no feedback or if there is no acknowledgement, then the timer will expire again. There is probably going to be a limited set of retransmissions. After that, packet or connection failure happens, and typically the sender will disconnect from the receiver. Okay. Now, the problem is, what happens in this scenario if A is actually has sent a packet to B? The packet arrives correctly. However, B sends an acknowledgement, and the acknowledgement itself is lost. That means A never actually receives feedback that the packet has arrived correctly at B. When this happens, the timer is going to expire, and then A will retransmit the packet. The problem here is B has now received the same packet twice. Up to this point, the transport layer at B has no way to differentiate that this is actually a retransmitted packet, other than actually examining its content. And we know that the transport layer doesn't read content. The transport layer only reads the transport layer header. And so you don't want to actually allow the transport layer to read content, because then the transport layers will actually now be interfering with each other's work. So you want the transport layer to be able to differentiate between the content of an original packet and the content of a duplicate packet. Here in this case, it will be a duplicate packet and B will not be able to differentiate. The solution to that is something called a sequence number. In each packet that A will send, it will add to it a sequence number. For each new packet, the sequence number will be a new sequence number. And so if a retransmitted packet is sent to B, then it will carry the same sequence number as an old packet. Okay? And so now B will actually be able to differentiate. If it's a duplicate packet, then it can just discard it and resend the acknowledgement. It, of course, has to resend the acknowledgement because eventually A has to get feedback that the packet has been delivered. Otherwise, it will keep retransmitting. Now, the question is, how many sequence numbers can we allow? We cannot actually allow the sequence numbers to increase to infinity, because at the end of the day, this will be a transport layer header and it will have a finite field to actually include sequence numbers. Okay. In this particular protocol, in stop and wait, how many packets do we need to differentiate? we typically need to differentiate only two packets, a new one from an old one, a duplicate one from a new one. Okay, so we need only to differentiate between two packets, and so one bit will actually be enough. If it is a 0, let's say A sends a packet, it will start with sequence number 0. If it arrives correctly, B will send the acknowledgement. It will say acknowledgement 0. Now the acknowledgement also has to have the sequence number. Okay. In this case, after that, A will send packet 1. Okay. B will receive it and will send acknowledgement 1. And then after that, A will send a packet with 0 sequence number again, and this is ACK 0. So the packets will keep alternating between sequence number 0 and sequence number 1. This is okay to use as long as A is not allowed to send a new packet before receiving an acknowledgement for the old one. That means A will not be allowed to send packet 1 before receiving acknowledgement 0, and will not be allowed to send packet 0 again before receiving acknowledgement 1. This means that B will be able to differentiate between this packet 0 and the original packet 0. Why? Because there is packet 1 in between. Okay. Because A received acknowledgement 1, it knows that the next packet should actually have a sequence number 0. Now consider this scenario. You have A sending a packet to B. It has sequence number 0. Acknowledgement is sent, but the acknowledgement is lost. Eventually, the timer will expire at A and it will resend packet 0. So this is fine. Why is it fine? Because B is now expecting packet 1. If it receives packet 0, it knows that this is a duplicate because now it's expecting packet 1. It has already sent acknowledgement 0. B will keep track. Okay. So in this case, B will just respond with acknowledgement 0 and it will discard this packet. Eventually, acknowledgement 0 will arrive at A and it will then send packet 1, and B will send acknowledgement 1 and so on. This is called the stop and wait protocol. You only need one sequence number and you need the timer. And the timer is just for actually the outgoing packet, the packet that the A has not actually received an acknowledgement for. The problem with the stop and wait protocol is that it will induce too much delay. Imagine you have two devices communicating on the opposite sides of the world. One device will send a packet and it will not send another packet until it receives the acknowledgement for the old one. And we know that this bottleneck is called the round trip time, and there is no way around it. If it's a large geographical distance, then there is really no way to decrease it. So we will now discuss the modifications that TCP do to the stop and wait protocols in order to actually improve its efficiency. The first and the main modification is called pipelining. We discussed pipelining in HTTP. Now we actually discuss it in TCP as well. TCP doesn't actually use the stop and wait protocol because it induces too much delay. It allows actually many packets to be sent before receiving an acknowledgement to anyone. There will be a window, and we will discuss this when we are discussing flow control. There will be a window of fixed size, and TCP is allowed to fill this window with packets. Okay, if the window is full, then the sender has to stop until more acknowledgements actually arrive. But as long as the window is open, the sender can actually keep sending packets to the destination. Okay, and acknowledgements will come back from the receiver as packets are delivered. How does this actually reduce the delay? Consider these examples. Consider actually the figure on the right. This one has no pipelining. So the first packet is transmitted at t equals 0, and we know that it takes L over R to transmit the packet. This is the transmission delay. L is the length of the packet, and R is the transmission rate. Once the packet is fully transmitted, it will travel, and it will take one round trip time for the response to come back, as you see here. So the total delay is round trip time plus L over R, as we know. So if we want to calculate the efficiency of this process, the efficiency is basically how much time did you actually use the communication channel. What is the percentage of time where the communication channel was actually used, and how much time was it just sitting idly waiting for the response or the acknowledgement to come back. L over R seconds. This is the time when the sender was actually busy sending a packet. For the remaining RTT, For all this time, the sender was not actually doing anything. It was just waiting for the acknowledgement to arrive. So this RTT that the sender has waited is idle time. It is nothing. The sender was actually not doing anything. So the percentage of the time that the sender was busy doing something, which is actually the efficiency or the utilization of this stop and wait method, is L over R over RTT plus L over R. L over R is the busy time. RTT plus L over R is actually the total time. So it's the busy time over the total time. If we try to actually put some numbers to get context, let's say L is equal to 8,000 bits. R is a very fast connection, 1 gigabits per second. That means you have purchased the fastest internet connection out there. The round trip time is 30 milliseconds, so it's not actually very long. The utilization will be 0.00027. That means that you sent 8,000 bits in 30.008 milliseconds. 30.008 is actually the round trip time plus L over R. So you have L and R, you do L over R, and the total time is 30 milliseconds, which is the round trip time, plus L over R, you get 30.008 milliseconds. In these 30.008 milliseconds, you were able only to send 8,000 bits, giving you an effective rate of 267 kilobits per second. That's just 8,000 over 30.008. So even though you have purchased a fast internet connection of 1 gigabits per second, you end up only sending at a speed of 267 kilobits per second, which is obviously a very disappointing rate. And this is not because of the speed of your connection, not because of congestion, not because of anything actually in the internet, other than the fact that you are using stop and wait. You are sending a packet and you are waiting for the response to come before sending a new one, which is causing a significant degradation in the internet speed. Let us say now you have pipelining, so you're allowed to actually send several packets, as you see in the figure on the left, before receiving the acknowledgement. And so in the same round trip time, here you will be sending 3 packets. So now the busy time is what? The busy time is that the time the sender is actually busy sending packets is now 3 L over R. Okay, because you're sending 3 packets, each one takes L over R to be sent. The total time is still the same. So the total time is still RTT plus L over R. That means in the same round trip time, instead of sending only 1 packet, you sent actually 3 packets. So the utilization has suddenly tripled. The utilization is now 3 times what it was just by actually including pipeline. So you see how pipelining is a very important process. So TCP doesn't use stop and wait. It uses a pipelined process to actually send data. And now we can actually take a look at the TCP header to learn how reliable data delivery is actually done. This is actually the header. This is the one that is added on top of the application data. So you see here that it still has the source and destination port numbers. Each one is 16 bits. Now you have 2 fields, each one 64 bits. These are for the sequence number and acknowledgement number, and we will discuss them in a little bit. There are also other fields. So there is a checksum that is used to check for error. There is a header length that contains the total length of the header. And there are a set of flags, U, A, P, R, S, and F. R, S, and F are used for connection establishment and termination. So if you want to establish a connection, you set the S flag to 1. This is called the SYN flag. The R flag is the reset flag. That means you're resetting all the buffers in the connection. And the fin flag or the F flag is the one that you set to 1 if you want to terminate the connection. Okay. There is a field called the receive window. This is used for flow control. We will discuss it later. And there is something called an urgent data pointer. If there is actually a portion of the application layer data that is urgent, that means you want to actually the application layer to have it first, you set the U flag to 1, and then the urgent data pointer will point to where exactly is the start of this urgent data. It's just a feature in TCP. Okay. So you see here in this header, all these fields are added. TCP will not pick and choose. That means all these fields will be added to every single packet that is generated, and if the application layer is using TCP. Okay. You see also that every header will have a sequence number and all packets that are sent between the devices will have a sequence number and acknowledgement number. What if you have a unidirectional communication? That means only A is sending to B. A will send a packet and B will send the feedback, which is the acknowledgement. But every header needs to have an acknowledgement number. That means even the headers that are sent from A will also have acknowledgement numbers. So even if it's a unidirectional communication, all the packets that will be sent from the sender will also have an acknowledgement number. Now the question is, what is the sender actually acknowledging if it has not received anything from B, if it is unidirectional communication? The answer is nothing. It will not actually be acknowledging anything. The field cannot be removed from the header. It has to be there because the header structure is fixed. So the field cannot be removed. So what will happen if A is not actually acknowledging anything? The acknowledgement flag here, the A flag, will be set to 0. If you set the A flag to 0, it means that the acknowledgement number is not actually acknowledging anything. It's just a dummy value. If you set it to 1, that means you are actually actively acknowledging something that you have received from the other side. There is also an options field. It can actually include optional information. It doesn't have to be there. It means this field actually can be removed. Can include something like the timestamp for the packet or information related to whatever, something between the sender and the receiver. So now we can discuss how the sequence numbers and acknowledgement numbers are chosen. TCP will receive actually from the application a set of bytes, a set of unnumbered bytes. TCP will divide these bytes into segments. That means, for example, it will take the first 1000 bytes and make one segment, as you see here. And then they take the second 1000 bytes and make the second segment, and so on. Take each 1000 bytes and make it into a segment. The 1000 bytes are just an example. It can actually be any number of bytes. Okay. Now, the TCP protocol will number these bytes, and the sequence number will be the number of the first byte in that segment. That means for the first segment, the sequence number will be 0. In the second segment, the sequence number will be 1000. In the third segment, the sequence number will be 2000, and so on. So the sequence number is always the number of the first byte in that segment. So again, TCP will receive all the bytes from the application layer unnumbered. It will number the bytes in sequence and create segments. So it will take a group of bytes and make this into a segment. And the sequence number will be the number of the first byte in that segment. The acknowledgement number, on the other hand, is always the number of the next byte that the receiver is expecting to receive in the right order. To understand what this means, let's actually take an example. Let us say here, you have this is device A and this is device B. A has sent the first packet. Let us say this packet is carrying sequence number 0 and is carrying the bytes from 0 to 999. Okay. Let us say this packet has arrived correctly, and so now B has the bytes from 0 to 999. If these bytes have all arrived correctly, actually, meaning without errors, and if they are in the right sequence, that means there is nothing B was expecting before them, then B will send the acknowledgement number for the next byte that B is expecting in the right order. Now, after 999, what is the next byte that is B expecting in the right order? It's actually byte 1000. And so B will send acknowledgement 1000. Acknowledgement 1000 means that B has received all the bytes from 0 to 999, and now it is expecting 1000. Once A receives that, it will send the next segment. Let's say the next segment now has sequence number 1000. And let's say it's carrying the data from 1000 to 1499. Okay. So now B, in addition to having the bytes from 0 to 999, now it has also the bytes from 1000 to 1499. Okay. Now, after that, B will find that it has this contingent block. It has the full block from 0 to 14 and 99. So what is the next byte that B is expecting in the right sequence? This will continue. Now let's see what happens when there is an error. Let us say, for example, that A sends a packet 0 to 999. This one is received correctly, so now B has the bytes from 0 to 999. Acknowledgement 1000 is sent. Now let's say A sends 1000 to 1499, of course with sequence number 1000. Okay, let us say this packet is lost. Okay. Now, because TCP is using pipelining, it will not stop. It's actually not waiting for a response. So it will continue. That means it will send the next packet, which has, for example, sequence number 1500 and is carrying the bytes from 1500 to 1999. Let us say this packet arrives correctly. Now, B will have the bytes from 0 to 999, which arrived in the first packet. And now it will have the bytes in the second packet, which is 1500 to 1999. Now B will detect that there is a gap between the first set of bytes and the next set of bytes. However, B will have to respond with an acknowledgement. B will have to send an acknowledgement in all cases. So B will respond using the same rule of acknowledgement that it knows, which is that the acknowledgement is for the next byte that B is expecting to receive in the right order. And in the right order is actually the key word here. What is the next byte that B is expecting in the right order? It is not byte 2000 because there is a gap. So the next byte that B is actually expecting in the right order is still byte 1000. So B will send acknowledgement 1000, indicating to A that the next byte that B is expecting is actually still 1000. It doesn't tell A whether this packet here, the one with sequence number 1500, was lost or not. It could also be lost. A will not know. But it is telling A that there is a gap. Now, because A is using reliable delivery, that means there will be a timer. That means when the first packet is sent from 0 to 999, there will be a timer for this packet. Once acknowledgement 1000 is received, then the timer for the first packet will be cancelled and there will be a timer for the second packet. Okay. Now, eventually the timer for the second packet will expire, and now A will send actually or will retransmit the segment that has expired again. So this will be 1000. And it will carry the data from 1000 to 1499. Okay. Once this is delivered, okay, so now B will have the bytes from 1000 to 1499. Now B, what does it have? It already got 0 to 999 in the first segment, and it already got 15 to 1999 in the second segment, and now it has 1000 to 1499, which fills only part of the gap, or actually fills the entire gap between 999 and 1499. So now it means that B has all the values from 0 to 1999. And so B, when it sends the acknowledgement for the retransmitted packet, it will follow the same rule. It will send the acknowledgement for the next byte that it is expecting to receive in the right order. Now, what is the next byte it is expecting to receive in the right order? It has 0 to 999, it has 1000 to 1499, and it also has 1500 to 1999 because it was received before and there was a gap. So when it sends an acknowledgement, it will send now acknowledgement 2000, indicating that it has all the bytes from 0 to 1999. This means that the acknowledgements in TCP are cumulative. That means an acknowledgement doesn't just acknowledge this packet, it acknowledges all the bytes before it as well. So when you receive acknowledgement 2000, that means all the bytes from 0 to 1999 has been delivered correctly and in the right order. That means there are no gaps. When you receive acknowledgement 1000, this is an indication that the bytes from 0 to 999 and without a gap. What would happen if you have, for example, 0 to 499. So we have 0 to 499 here. And then you have 490, you have 500 to 549. And then you have 550 to, let's say, 699. And then you have 700 to 999. So let's say the first one arrives correctly, the second and third one are lost, and the fourth one arrives correctly. So now there is a gap. Okay. B doesn't know whether this gap will be filled by one packet or not. It just knows that there is a gap in bytes from 500 to 699. What will happen if the second packet, okay, this packet here, packet with a sequence number 500, this timer expires and eventually this packet will be transmitted or retransmitted, and now B will have the bytes from 549 as well. Okay, from 500 to 549. So now what does B have? B have from 0 to 499, 500 to 549, and 700 to 999. When it sends an acknowledgement, what will be the acknowledgement? The acknowledgement will actually be for the next byte that B is expecting in the right order. What is actually that? B has 0 to 499, and now it also has 500 to 499. It also has 700 to 999, but there is a gap. So when it sends an acknowledgement, it will be acknowledgement 550. When A receives this, it will know that the second packet has also been, the retransmitted second packet has been delivered correctly. Eventually, the timer for the third packet will also be will also expire, and now A will send or will resend packet from 550 to 699, and then A will have it, and now A will also have from 550 to 699. And so now B has everything. B has from 0 to 499, has 500 to 549, 550 to 699, and also has 700 to 999. And so the next acknowledgement will be acknowledgement 1000, indicating that the entire block has actually been delivered correctly. Now, what will happen if you have something like that? 0 to 499, and then you have 500 to 549, and then this one is lost, 550 to 699, and then the fourth one actually arrives correctly to 999. Now, when B receives the first two segments, it will respond here with acknowledgement 550. Okay, so it's important to note that the acknowledgement is always for the next byte that B is expecting in the right order. Okay. We can see some additional examples here. Let us say host A sends a packet with sequence number 92 and is carrying 8 bytes. The acknowledgement for that will be acknowledgement 100, because this packet will have byte 92, 93, 94, 95, 96, 97, 98, and 99, indicating that the next byte is expected to be received is byte 100. If the acknowledgement is lost, then A will not know that the acknowledgement is lost. The timer will eventually expire and will retransmit the packet. Not a problem. B will receive it and will just retransmit the acknowledgement again. When B retransmits the acknowledgement, it doesn't actually think that it's retransmitting the acknowledgement. It just follows the rule. What are the bytes that I have? What is the next byte that I'm expecting to receive in the right order? Here it is. In the example on the right, A sends two packets, one with sequence number 92 and has 8 bytes, one with sequence number 100 and has 20 bytes. The two acknowledgements are sent from B. Let us say that the timer was set for a very short value. That means host A sets it to a very short value, and it expires before the acknowledgements arrive. And the timer always expires just for one packet. That means you never actually set a timer and you retransmit two packets at once. The timer is always for the oldest unacknowledged packet. So this would be the packet with sequence number 92. If the timer is, and then host B will receive the duplicate, and it will indicate that it's a duplicate because it's carrying an old sequence number. And so when B sends an acknowledgement, it will follow the rule. The next byte that it's expecting to receive in the right order is 120. Now, when A receives 120, it will not think that B has just only received the second packet. It will think that B has received everything, because acknowledgement 120 is cumulative. That means it acknowledges all the bytes before it. That means B is telling A that I have received the bytes from 100 to 119, and I have also received the bytes from 92 to 99. Okay, you have to always remember that the acknowledgements are cumulative. Last example, let's say host A sends a packet sequence number 92 and having 8 bytes. The acknowledgement is sent, but the acknowledgement is lost. And then A sends a second packet, which is carrying sequence number 100 and having 20 bytes. When B receives the second packet, it will respond with acknowledgement 120. A will receive acknowledgement 120 and will think that the two packets have arrived correctly, even though the first acknowledgement was lost. This is again because acknowledgements are cumulative. Last thing I will discuss with you today is a feature in the reliable delivery mechanism of TCP that is used to reduce the time associated with retransmitting a packet or the timeout. The problem with the timeout is that it's very difficult to set it to an actual or a correct value. If you think about it, what is actually the suitable value of a timeout? Okay, or how would you set the timer for a packet? You want it to have enough time for the packet to make it to the destination and for the response to come back. That means it has to be a little bit greater than the round trip time. If you set it too short, then it will expire too soon. The acknowledgement could well be on its way, but you set it too short, and so you will retransmit. This is not a problem. That retransmission will be detected as a duplicate, and it will be discarded, and the acknowledgement will be transmitted again. Everything is fine. However, it consumes the resources of the communication medium. It's just not efficient. If you set it, on the other hand, for a too long time, if you set the timer for a packet to be retransmitted for a very long time, the problem with that is the packet would be lost and you would be waiting idly for a very long time before actually retransmitting. This is also wasteful. You want it to actually be the right value. You want it to be exactly equal to the round trip time. But the problem is, as we know, the round trip time is not a constant value. It's only an estimate. The round trip time depends on the queuing delay, depends on the path, depends on the congestion. And so the round trip time itself is changing. So how can you actually set a timer that is effective? TCP gets over this fact by separating actually two events. It could be that the channel between you and the destination has a very low quality. That means anything you send will be lost. But it could also be, and it's the most likely scenario, that it had just a momentary lapse. That means there was just a small error and the channel has recovered. TCP has actually a mechanism to deal with this issue. And the mechanism is called fast retransmit. It's actually illustrated in this figure. Let's say host A sends a packet with the first sequence number. This is not sequence number 1. This is just the first sequence number, whatever it is. So with the first sequence number, host B will reply with the first sequence number. Host A will send a packet with the second sequence number. Let's assume that this packet is lost. So it never makes it to B, and so B doesn't send anything. Now A will send packets 3, 4, and 5. These 3 packets arrive at B, and B will detect that there is a gap because the second packet has not arrived. And so when B sends an acknowledgement, the acknowledgement will follow the rule, the next byte that it's expecting to receive in the right order. And so it will be identical to the acknowledgement for the first packet. And so now host A receives 4 acknowledgements carrying actually the same number. The original acknowledgement for the first packet and 3 duplicate ones. Once A receives 3 duplicate acknowledgements, that means it receives 4 acknowledgements for the same number after each other, it will indicate that there is a problem. It will indicate that the packet has been lost, and so it will resend the packet. The advantage here is this is done even before the timer for packet 2 expires. That means here the timer for packet 1 expires because the acknowledgement for 1 has been received. And so here the timer for packet 2 will start and it will expire here. However, once A receives 3 duplicate acknowledgements, it will resend packet 2 directly, and so packet 2 will now be received here, and so it can actually send acknowledgement 5, indicating that all the packets have been delivered. So fast retransmit allows the sender and the receiver to recover quickly from errors. Other than waiting for the timer, which is typically set for a long time, you can actually resend faster. And this is very beneficial if it's the case where the channel just has actually a small error, just one packet is lost. And so now you can actually set the timer comfortably to a longer value, just to make sure that you are not actually retransmitting too soon, and you rely on fast retransmit to recover quickly from errors. This ends the discussion of the reliable delivery mechanism, and so we will stop here today, and next time we will continue the discussion of the services in TCP.